So now we'll go into the second section of Module 4. This will be Module 4.2. Within this module, we're going to continue on with conduction analysis, dealing with 1D steady-state conduction, but now we're going to take a look at some radial systems here. So topics we're going to cover for these radial systems, we'll take a look at some of the theory and key equations, a couple different applications utilizing radial systems, and then get into some problem solving while I'll go through some of my hand solutions to these problems. So as we begin looking at radial systems here, the first one we want to take a look at is the tube wall. So now in the diagram below, we can see we have a tube here, has an inner radius right here of R1. We have an outer radius here, the outside of this guy here, of R2. And we can see, contrary to the plane wall where we had a fluid on one side or the inside and outside of a plane wall, now we have it on the inside and the outside of the tube here. So what we can see is we have this hot fluid. We have the properties T infinity 1, H1, as it's going through the center of this tube right here. So this is our fluid number 1 going through the center of the tube with radius R1. And then on the outside over here, we have the cold fluid with a temperature of T infinity 2 and an H2 value here for convection on the outside of the tube there. So that's the difference between the plane wall and the tube wall as far as our diagram goes. Rather than being on one side of the wall and the other side of the wall, now we're on the inside of the tube and the outside of the tube. Now with that there, we can see at this surface, at the inside of the tube there, we now have this surface temperature TS1, and on the outside of the tube here, we now have the surface temperature TS2 associated with those there. We can see that this tube has a length given to us as L right there as well. Now what we want to do from here is to try to break this down and look at it in a 2D image, simplified down so we can understand what's going on and draw out our thermal circuit. So we come up here, we take a look at this, we draw out this diagram over here, where we can see this right here is our inner surface right there, here is our outer surface right there, where R is the distance from the dead center of our tube right here. So we go out, and when we hit R1, that is this surface right here, our inner surface, R1 right there. So at R1, we know our surface temperature at that inner surface is TS1. Then we go out here to a radius of R2, which is our outside surface right here, our outer surface of our tube right there, and that has a temperature right here at that surface of TS2. Now having this diagram like this really does help us to draw out our thermal circuit down here. So we can say if we start at 1, R1 right here, at the inside of this right here, we can say, well, going on the inside of this tube, we see we have this hot fluid here, so we have convection occurring. So if convection is occurring, that's what this step is here, from temperature T infinity 1 to TS1, which is the fluid temperature, inside fluid temperature, to the inside surface temperature here. So we have this relationship here. We have 1 over H1 times 2 pi R1. Now R1 relates to that inner radius right there, times the total length. So that's your convection term there. Then we say, okay, if we go from TS1 to TS2 right here, well, that's going through this right here. That's going to be conduction going through the thickness of that outer wall right there. So that has this relationship here of the natural log of the ratio of R2 over R1, all divided by 2 pi KL. So we have that information there, and that's again for the conduction occurring through the thickness of that wall right there. Then we get to the outer surface of the wall, here where we have our TS2. And we can see at TS2 down here, the outer surface of the wall right there, we now have this interacting with our cold fluid, which has T infinity 2 and H2 right there. So now we again have convection occurring right here. So we can see this is 1 over H2, 2 pi R2L right there. So we have convection, conduction, convection. We draw out our thermal circuit the same way we would for the plane wall there, but now we're doing it for the tube wall. Again, the difference now is we have these radiuses, and we have the inner fluid temperature and the outer fluid temperature. So now let's take a look at some of the governing equations associated with the tube wall here. So you can see I've redrawn out here, we have our diagram over to the right here for our tube wall that we just saw on the previous slide there. Now we can see our governing heat equation that we're going to utilize for the tube wall is given by equation 3.28 in our textbook here. We have this relationship here. We have 1 over R. We're going to recall R is that radius here starting from the center of our tube wall and moving out like this. So that's why we hit here, that's our R1, we go all the surface, that's R2. So any distance we're coming out from that center right there is our R distance there, times DDR of our K, our thermal conductivity, times that radius R over dt dr, the change in temperature with respect to that radius, is equal to 0. So that tells us a lot within that equation there. So what this does is it dictates that the quantity of KR dt dr is going to be independent of R, and that's why that's equal to 0 right there in our heat equation there. So now we'll move on to the next equation here. Now, what we think about here is that the rate at which energy is conducted across any cylindrical surface in the solid, we have this QR term right there for our heat rate right there. And this is negative Ka, our negative thermal conductivity times our area right there times dt dr, the change in temperature with respect to that radius, is equal to, now we have this relationship down here from equation 3.29, we have that negative K, then we have for our area for this right here, we're dealing with a cylindrical surface, is 2 pi RL dt dr. So all we're doing is we're replacing this for our area for a cylindrical surface with this relationship right here. Now what we can kind of infer from this equation 3.29 is that the conduction heat rate right here, our heat transfer rate QR, but not the heat flux, is constant in the radial direction. Now from there we can go on and find that our temperature distribution for a constant value of K right here, if that K doesn't change, is given by the following equation down here, 3.31 in our textbook here. We have T of R, our temperature with respect to that R value there, that radius is coming out from the center of the tube wall, is equal to now our temperature difference between surface 1 and surface 2. And recall here our surface 1 is our inner surface TS1, our surface 2 is our outer surface TS2, where the hot temperature is at the inner surface and the cold fluid at the outer surface right over there. This divided by the natural log of that ratio of R1 over R2, where R1 is the inner radius and R2 is the outer radius, times the natural log of R divided by, R being any distance from that center of the tube wall, divided by our outer radius R2, plus that outer surface temperature TS2 right there. And again, this goes back to 3.31 in our textbook. So continuing on looking at some of our governing equations related to the tube wall here, we can now take a look at heat flux and our heat rate right here. So for our heat flux equation, our Q sub R double prime is equal to that negative K thermal conductivity times that change in temperature dt dr with respect to that radius is equal to, now we see here our thermal conductivity divided by that radius, which is from the center moving out of the tube wall, times the natural log of the ratio of our inner and outer radius right there, R1 over R2. And this is all time the temperature difference between the inside and outside surface temperatures of the tube right there. And we pay attention now, we're in units of watts per meter squared. Now, if we're talking about the heat rate per unit length right here, now we can see we have our QR prime. This is equal to 2 pi R times QR double prime, or our heat flux right there. So basically, we're taking our heat flux equation from the top here and multiplying by 2 pi R right there. So we go through and now we can see that this is equal, when we multiply through by that, we now have 2 pi K divided by the natural log of the ratios of the inner outer radius times the difference in those surface temperatures there. And now, rather than being watts per meter squared, we've multiplied through by a length right there. So now this is going to be watts per meter. Now, last, we can take a look at just our heat right here, our Q sub R. This is equal to 2 pi RL times our heat flux there. So now we're multiplying through by a meter squared, as we're going through from our heat flux equation right there. Now we see we have 2 pi L times our thermal conductivity K divided by the natural log of that ratio of our outer and inner radius right there times the surface temperature difference from the outer and inner surfaces right there. And now our meter squared goes away and we're just left with watts here when we're dealing with our heat right there, because we've multiplied through by that meter squared term, or our area. Now, if we can take a look next at our conduction resistance right here, and we're going to do that for R sub T conduction right here, and we're going to do it per unit length as well. So for RT conduction right here, relating back to equation 3.33 in our textbook, we can see this is equal to the natural log of the ratio of the outer and inner radius, R2 divided by R1, all divided by 2 pi RL, there's our area there, times that thermal conductivity K. Now, per unit length, we can go through again, and now the only difference is that L drops out of the bottom there. This is equal to the natural log of that ratio of R2 divided by R1 over 2 pi K. So next, let's take a look at a composite tube wall right here. So we're going to make the assumption here that there's negligible contact resistance to keep the problem simple at first, and we're just going to look at the fact that it is a composite wall. Now we have materials A, B, and C that we can see over in this diagram over to the right, and we can see what is our governing equation for heat rate. Well, we have Q sub R is equal to T infinity 1 minus T infinity 4. We'll come back to our diagram over here, and we can see T infinity 4 is on the outside fluid temperature over here, and T infinity 1 is our inside fluid temperature right there within our composite tube. Now we can see this is all divided by our total thermal resistance right here, our R total. Now recall we do have a relationship between R total and U, so we can substitute that in this equation 3.35 in our textbook then becomes UA times that temperature difference between our inner T infinity 1 fluid temperature and our outer T infinity 4 and fluid temperature there. Now recalling that relationship right here, U sub A is equal to 1 over R total. So that's why we can have 1 over R total there, becomes a U sub A right there. Now this is a constant independent of radius, but U in itself is tied to a specification of an interface right there. We have our definition right here from 3.37 that U sub I is equal to A sub I times RT inverse right there. So 1 over AI times our total thermal resistance right there. So now from here, we're going to take a little bit closer look at this diagram. So taking a little bit closer look at this composite tube wall, what we want to do is figure out how we can look at this in a 2D situation, relate it back to our 3D diagram of the realistic case, and from there, draw out our thermal circuit associated with these composite layers. So we can see here over on the right, we have our 3D representation of the realistic composite tube. So we have here the total length right here is L. We have our inner fluid temperature right here of T infinity 1 and a H1 value there. And we have an outer surface temperature right here, T infinity 4 and an H4 value right there. Now we can see there's our composite wall right there of these different layers within our tube. So from this here, what we want to do is draw this as a 2D representation. The same thing we've done with just a regular tube wall right there. So we come over here, but now we have these different materials right here. We have material A, B, and C related to those different layers within the tube wall. So we can see now each of these is going to have a distance from the center of our tube right there. So this is the distance right here. So R1 is the inner surface temperature right there. R2 goes to our surface temperature right here, which is between material A and material B. R3 goes to our surface right here, which is in between material B and material C. And R4 goes out here to our outer surface right here, which is the interface with our outer fluid over here. So with that there, now we have information related to where each of the R values are from the center of our tube to each layer within the composite wall right there. Now for each of these here, I'm going to draw out a line straight down. So I have my fluid temperature over here, T infinity 1, I draw that straight down. I have my TS1, which is TS1, we can see here, that is the temperature of surface of material A on the inside of our tube right there. Then we have our TS2, our T2 right here, which is our temperature right here. Sorry, not TS2, just T2, which is the temperature between interfaces of A and B material right there. So that's my T2. And T3 is my temperature between materials B and C. That's my T3 right there. And then my TS4 is my surface, my outer surface temperature right here, TS4. So I draw all those out. I also have my fluid temperature inside and my fluid temperature outside right there. So we can see we have a node right here for our fluid temperature on the inside, a node right here for our inner surface, TS1, a node right here for the surface in between A and B, a node here for the surface in between B and C, a node right here for the surface, the outer surface right here at the edge of C, and then we also have a node right here for our outer fluid temperature, T infinity 4. Now with those right there, we can go through and draw out this thermal circuit. So we say, okay, what's going on between each of these? Between T infinity 1 and TS1 right here. So that's our outer fluid temperature and our inner surface temperature right there. So that is going to be convection. So this is our convection term right here. We have our general governing equation for that there. So for convection right there, we have 1 over H1 2 pi R1L from our governing equation there. Then we go between TS1 and T2. So right there, this is going to be conduction. So we're going just through material A for that right there. That's just going through material A, so that's conduction right there. So for conduction, we have the natural log of the ratio of those radiuses. Now this is where it's a little bit different here. What radius are we dealing with? This is R1 and R2. So R1 is the inner radius on the inside surface right there. R2 is on the outside of material A. So that's what the R1 and R2 are for a composite tube wall right there. Now this is all divided by 2 pi times KAL right there, where Ka is our thermal conductivity of material A. So now we go between T2 and T3. So between T2 and T3, we're dealing with material B right here. So again, now we have the natural log of conduction. So we have the natural log of the ratio of those radiuses. And now we look here, this is R3 and R2. If we're looking at those radiuses associated with material B right there. And this is divided by 2 pi times the thermal conductivity of material B times that length L right there. Then we go between T3 and T4, still conduction going on now through material C right here. We're dealing with R3 and R4 now for this here. So we have the natural log of R4 divided by R3 all over 2 pi times Kc, the thermal conductivity of material C, times that length L right there. Then we get between TS4 and T infinity 4. So this is where now we have our outer fluid temperature right there, T infinity 4 and H4 right there. So this is convection again. So we have our general equation for convection. So we have 1 over H4 times 2 pi R4 times that length L. And that is now our equation for our thermal circuit related back to our given diagram. So we can see it's really important to go from this initial 3D diagram, draw out a 2D representation, make it nice and big so you can clearly understand everything that's going on, your fluid temperatures, where conduction occurs, where convection occurs. From that, directly below it, use your lines, draw out that thermal circuit, drop the node straight down, and ask yourself each step between the way, between this surface and this surface, what's going on? Okay, this is my governing equation, and plug it in. Now from here, we're going to move on to our spherical shell. So we can see here we have our given diagram over here for a spherical shell over here. Again, it's just a 2D representation of it, and we can come out of the shell with a small element that we'll deal with there. Before we get into too much of the diagram, let's first take a look at our governing equation. So our heat equation, if we're dealing with a spherical shell, is given by this relationship right here. 1 over r squared times d over dr times that r squared times the change in temperature with respect to r, dt dr, is equal to 0. Now, what does this tell us? What does this form of heat equation tell us about the variation with r? Well, what this tells us here is that qr is a constant, and this is going to be independent of r. Now, what is r? R is that distance as we go from the center of our sphere right here moving out. So we can see if we get to our inner surface right here, that's an R1. We get to our outer surface here, that's an R2. But any distance that we're interested in here for this element was here as some distance r out there. Now, other special case that we can look at here is temperature distribution when we have a constant K, so it's just one material with one thermal conductivity associated with it. If that's the case right here, our temperature distribution, or our temperature with respect to that radius r as we move out from the center of our sphere right here, is equal to our TS1. What is our TS1 right here? We can see, go back up to our diagram here, our TS1 is that inner surface temperature right there, minus TS1 minus TS2, so that inner surface temperature right there, and our outer surface temperature of the sphere, TS2, and that's all times now, right here on the top numerator up here, 1 minus R1 over R. Now this ratio of r's right here, your R1 is your inner surface radius right there, and your R is the distance to whatever element you're interested in right there, all divided by 1 minus the ratio of R1 over R2, where R1 again is that inner radius to that inner surface right there, and R2 is the radius to the outer surface right there. So this is your temperature distribution for the case where you're dealing with just one value for K, and it's a constant K value for that material. Now going back up to our diagram up here, we've already discussed most of it, but if we want to zoom in on this small element here, we can now assign variables for dimensions associated with that there. So we have our heat rate, Q sub r right here, going into it, and then coming out of it, we have Q of r, our QR, plus a dr here, where we have our dr down here is the thickness right here, our delta r right there, associated with this element that we're taking a look at, this distance r away from the center of our sphere. So this now brings us to some governing equations we can utilize when we're dealing with these spherical shells. So if we're talking about heat flux, heat rate, and thermal resistance governing equations right here, we can reference back to our textbook equations 3.40 and 3.41. What we have here is for our heat flux, our QR double prime, this is equal to our negative K, thermal conductivity, times the change in temperature with respect to that radius, dt dr. Again, that r is going from the center of the sphere moving out. And this is equal to, we can plug in now, K divided by, now if we're taking a look at this relative to those radiuses in the sphere right here, we have our r squared, that distance out from the center of the sphere, times now here we have 1 over R1, which is the radius of the inner surface, minus 1 over R2, where R2 is the radius to the outer surface right there. So subtracting those two right there and multiplying by R squared on the denominator. And this is all times the difference between the two surface temperatures, between our inner surface temperature, TS1, and our outer surface temperature, TS2. Now, if we recall what we want to do to go from our heat flux to our heat rate, we're multiplying through by that A term right there, where our A term for a sphere right here is 4 pi r squared. So we're just taking 4 pi r squared, multiplying it through by our heat flux up top, our QR double prime right there. So that's what we do there. And when we plug that in, multiply through by our 4 pi r squared, we end up with is on the numerator, we have 4 pi k right there. And then we can see some things cancel out with the r squared there, cancel with the r squared there. We have on the bottom just a difference between 1 over r1 minus 1 over r2, where r1 is the inner surface, the radius to the inner surface, and r2 is the radius to the outer surface there, times that temperature difference between our inner surface and our outer surface, Ts1 minus Ts2. And last, we can take a look at our thermal resistance, our R sub T for conduction here. This is equal to, on the numerator, we have that 1 over R1 minus 1 over R2, the same thing we've seen from before up there. And now this is divided by 4 pi K. So this is our thermal resistance for conduction. Now, what if we had a composite shell? Well, if we did have a composite shell, it'd be similar to how we looked through our composite tube right there. We'll take a look now here. For our composite shell, what we have is our Q sub R is now equal to our delta T overall divided by our R total. And we go through that R total the same way we did and sum up all of our thermal resistances as we're going across the different layers, different composites within the shell of the sphere right there. This is equal to, if we plug in UA is equal to 1 over our R total, we have UA times our delta T overall is equal to our Q sub R. So again, that just right there tells us our UA is equal to the inverse of R1 total right there, which is a constant, but UI is going to depend upon our AI right there. So UI in itself is equal to our AI times our R total, all on the denominator, so 1 over that right there. So now let's work through a tube example problem here. So in example 3.50 from our textbook here, we have a stainless steel, they tell us it's going to be ASI 304 steel. The tube is used to transport a chilled pharmaceutical, and that tells us the inner diameter right here of 36 millimeters, and a wall thickness, they tell us, as 2 millimeters. Now the pharmaceutical and ambient air temperatures are given to us in the problem statement here as 6 degrees Celsius and 23 degrees Celsius respectively. Well, the corresponding inner and outer convection coefficients are, so they tell us our values here for our convection coefficients, our H values here are 400 watts per meter squared times Kelvin and 6 watts per meter squared times Kelvin respectively. So before we even get into what they're asking us to solve for, one thing that we know is they didn't give us initial diagram. They didn't give us variable names. So those are two things that we're going to want to do and do correctly. So up to this point, a lot of the examples we've looked at have all given us variable names, whether it's been in the diagram or in the problem statement. This one does not. It just tells us what they physically are. So this goes back to when I talk about that setup page, how those 4 things that we're looking for in our givens, we want to make sure we clearly define so we can reference back to them, because they're not always going to be in our problem statement here. So you're going to want the variable with its indices, what it actually means and how it relates to the problem, what the numerical values are, and what those units are. So those 4 things we're going to want to include in our given section for this problem here. So now we know what we're going to need to do. We're going to need to come up with those variable names, our correct indices, and our diagram here. So what are they asking us to solve for? They're asking us to solve for 2 different things in this problem. In part A, they're asking us what is the heat gain per unit tube length. And in part B, they're asking what is the heat gain per unit length if a 10 millimeter thick layer of calcium silicate insulation, so there's a layer of insulation here, and they give us the value, our K value for that insulation, if K is equal, our thermal conductivity for the insulation is equal to 0.05 watts per meters times Kelvin, is applied to the tube. So as I'd mentioned, one of the first things we're going to want to do as we're starting this problem here is take that information from our given problem statement in 350 right here and draw out an initial diagram so we can get a visual of what we have going on here. So they tell us right here that we have a stainless steel tube used to transport a chilled pharmaceutical that has an inner diameter of 36 millimeters and a wall thickness of 2 millimeters, but then also for part B of the problem, there's a 10 millimeter thick layer of insulation on the outside of it there. So what we have here is we have this inner radius from the center of our tube right here going out to right there. So that'll be our R1, and that has a diameter. So There's a couple things that we need to really pay attention to here. They're giving it to us in diameter, as all of our equations use radiuses. So immediately we're going to take half of that to go from 36 to 18. Then the other thing to be careful of is our units. Typically we want to be in meters for everything else. We can see all of our units here in meters, but for this here it's in millimeters. So for right now, I'm just going to leave this as millimeters, but we will probably have to convert as we plug into our governing equations. So we say our inner diameter, R1, is 18 millimeters, because that's half of our 36, it tells us right there. And I'm calling this R1. I'm coming up with the variable names and the indices for this here. Now it has a wall thickness of 2 millimeters. So that means it goes out 2 more in the radial direction, so it'd be 4 more in the diameter. So again, pay attention as you're doing this. We're not taking half of this. It just comes out 2 more. That's the thickness of the wall right there. So our R2 right here, as that thickness, the wall thickness right there, is now 20 millimeters from the center right there to get to our R2. And then if we're dealing with our insulation layer, this is 10 millimeters more than that. So we go past our 20, another 10 till we get out here. So we're calling this R3 is equal to 30 millimeters. Again, these are all in millimeters still, but now I have an R1, an R2, and an R3, where I know what those are. My R1 is that inner diameter. My R2 goes out to the wall thickness right there. My R3 goes out to the insulation right there. Now I've physically drawn this out, so I have a visual representation showing what those radiuses are as well. Now they tell us we have a pharmaceutical, is chilled pharmaceutical on the inside of this right here. So there in the inside diameter here, going through the center of our tube, is this chilled pharmaceutical. Now it does tell us it has temperatures for the pharmaceutical of 6 degrees. So there's 6 degrees Celsius right there. And it gives us our convection coefficients right here, our H values here for the inner and outer as well. For the inner, this is going to be 400 watts per meter squared Kelvin. So I write that down. HI, inner, is equal to 400 watts per meter squared Kelvin right there. And my temperature of this inner fluid right here, I'm calling T sub infinity I. So again, I'm coming up with these variable names and indices for this right here to relate back to the problem statement. Now they also tell us we have air on the outside, so here's our ambient air out here. Now we know our temperature of our ambient air is 23 degrees, so our T sub infinity outer is equal to 23 degrees Celsius. And we have our H value for our outer right here of 6 watts per meters times Kelvin right there. So there's our HO of 6 watts per meter times Kelvin right there. And then for part B, we have this insulation. It does give us a K value for our insulation right here on part B of the problem there, which is 0.05 watts per meter times Kelvin. So all I've done so far is give myself that diagram, that visual representation of all the information within the problem statement, and assign some variables and indices related back to those there. Now this is also going to be helpful to do this prior to even writing these down in my given section right here, so I can have something to reference and clearly understand, again, all 4 of those. The variable name with its indices, the numerical value, the units, and how it relates to the problem. And that's going to be a lot easier to see how it relates to the problem when I have this right here to reference back to. So now that we've had the opportunity to read through that problem statement, draw our diagram here from all the information given within that problem statement so we have a visual representation, what we want to do is take that information now and create this setup page right here. So I've clearly labeled dealing with problem 3.50. What is my given information? So now I can reference back to the problem statement and to this diagram that I have up here to start writing out information. So we can see R1. Now R1, which is the radius, the distance out to the inner surface right there, is given to me as 36 millimeters. So I can say, well, diameter D1 divided by 2 is going to give me R1 right there, where D1 is my 36 millimeters divided by 2 is 18 millimeters. I want to convert to meters, so this is therefore 0.018 meters. So again, double check. Do I have my 4 things? My variable name, R1. I have my numerical value, 18. I have my units, millimeters, and I have how it relates back to my problem right here, inner diameter. So I want to do the same thing for R2 and R3. So R2 is for the wall. For the wall here, this is going to be my R1 plus the wall thickness of 2 millimeters, which is 18 millimeters, plus 2 millimeters, which is 20 millimeters, or when I convert to meters, 0.02 meters right there for R2, which is the radius going to the wall. Then I have R3, which is for the insulation on the outside there. So this is my R2 plus this 10 millimeters of the thickness of the insulation. So this is 20 for R1 plus 10. I'm sorry, for 20 for R2 plus 10 for the thickness right there is 30 millimeters. Convert to meters. This is 0.03 meters. Now I'm taking a look at my pharmaceutical temperature right here. So there we have this given to us as 6 degrees Celsius right here. The variable I'm using for this here is T infinity I for inner. It's my inner fluid temperature right there. Now I want to convert this from Celsius to Kelvin right away. In case I need to plug that into other equations right there, I'm going to need to use it in terms of Kelvin for my unit. So this is 279.15 Kelvin, all right here on my setup page, so I can quickly reference back to it. I do the same thing for my outer fluid, T sub infinity O. My outer fluid is the ambient air. So the ambient air temperature right here is given to me as 23 degrees Celsius right there. I want to do the same thing, convert that to Kelvin as well. So I do this right here, 296.15 K. Then from there, what I can do is take a look at my convection heat transfer coefficient inner. So my inner H sub I right there is equal to 400 watts per meter squared times Kelvin. So again, with this units here, with everything in Kelvin here, so I went ahead for my two temperatures, the fluid temperatures, and converted those to Kelvin as well. Now my H outer right here is given to me for air right here, 6 watts per meter squared Kelvin right there. So 6 watts per meter squared Kelvin right here. So again, I write down this is for air, convection heat transfer coefficient. So I have how it relates back to my problem in my problem statement as well. So from next, I want to take a look at my K value for the insulation right here. So this is my thermal conductivity right here. My K value there for insulation is given to me in the problem statement is 0.05 watts per meter times Kelvin. Then I still also am going to need my K value for my actual wall right here, my K sub ST. So this is something that I'm going to need to look up. So they gave us in the problem statement that it was steel and the type of steel. So what we can do with that information is we can go to table A1 and look it up and interpolate for the correct temperature there in order to back out our K value right here for the steel, which ends up being 14.2 watts per meters times Kelvin. Now that we have all of our information given down, all of our given information, everything we've had to look up, everything we've had to convert up here, all in one location here in the correct units, now we're going to ask ourselves, what are they asking us to solve for? Well, we need our Q prime right here, our heat gain per unit length of the tube, and we also need our, in part B, our heat gain per unit length of the tube when we've considered this added insulation. So next from here, what we want to do is take a look at any assumptions we're going to make to simplify down our solution to the problem right here. So what assumptions do we make? Well, we can assume steady state conduction, 1D radial conduction, constant properties, negligible contact resistance between the tube and the insulation, and a negligible effect of radiation. So these are all the 5 assumptions that we're going to make to simplify down our solution to this problem. So now we have one nice page right here for our setup page. We have our diagram, we have our given information with all the correct units and variable names, and we know what we're looking for and any assumptions that we're making, so we can reference back through to this page as we're going through and solving out this problem. So now on our setup page, we talked about getting our thermal conductivity K value for that steel. So we can go into our table here and say, okay, this was the steel that we're looking at right here. We need to interpolate between 2 different temperatures depending on what temperature given. So our temperature is in between this. So we interpolate for 280. So we interpolate between 200 and 400. We put 280 in between there. We're going in between 12.6 and 16.6 for our K value right here. So we can do that interpolation. We do that interpolation from table A1 for that type of steel. This is where we get that K value of 14.2 that we saw on our first setup page. So now that we've had that opportunity to read through that problem statement, create our diagram, and create that setup page, we now have all the information that we need to begin the solution to our problem. So the first step in the solution to our problem is to create this thermal circuit. Now our thermal circuit, we're going to reference back to the diagram we created, and if you had created a 2D version of it as well, that is helpful, so you can draw it directly underneath it. When you draw it directly underneath it, it makes it easy for establishing these nodes here. So what we can see is we have the inner and the outer node right here that are relate back to the temperature, T sub infinity I, which is the temperature of our fluid on the inside, this pharmaceutical fluid, the cooling fluid there. Our T sub infinity O relates back to our ambient air temperature on the outside right there. So now the rest of the nodes right here are as we step from the inside of this inner tube right here out to each of these layers. So the first one we do is the inside layer of that steel. So between the steel and our ambient air, we have that layer there. Then we have the thickness of the steel. So then we have right here, our second node, our third node right here relates to where we're at, the 20 millimeters right here at the outside of the steel and the inside of our insulation layer right there. And then from there, we go to the outside of our insulation layer out here. We have our R sub 3 of 30 right there. And then from there, we go out again to our ambient air temperature out here. So those are our different nodes. We have 1, 2, 3, 4, 5 nodes. Inner fluid temperature, inside of the steel, outside of the steel, in between the steel and the insulation, and then we have outside of the insulation, and then we have our ambient air temperature right there. So all of those are our 5 nodes right there. We have to ask ourselves what's going on. Well, what's going on between T infinity I and the inside of that steel? Well, that's going to be our convection term right here. So that's R prime convection, because it's per unit length. We have that prime right there because they're asking us to solve for length. And that's convection right there. Then we have conduction going through the steel in this section here. Then we have conduction going through the insulation in the next section right there. And then after that, we have convection again from the outside surface insulation to the ambient air and the surroundings. Now, a thing to note with this thermal circuit that I drew out here is this is for the entire problem, including part B. But part A did not ask us to do anything with the insulation layer. So this thing we have right here for our insulation does not exist in our thermal circuit for part A. So I would suggest, rather than trying to do it all in one like this, solve them separately. Do out part A without that insulation, draw out a separate thermal circuit. I know it's a little bit more work and a little bit more time, but as you can see here, if I try to do this all in one, so I've done 2 things here on purpose. 1, I did these thermal circuits all in one to show you it can get a little confusing. And 2, I did not draw out my 2D layers from my 3D diagram here to drop down those nodes, so we can see it is a little bit confusing, especially if there were even more layers within this composite wall of where my nodes are and what those physically mean. Whereas if you have that 2D representation, you can draw a line straight down at each of those interfaces, each of those surfaces. It's a lot easier to create this thermal circuit right here. So just something to think about, kind of showing you if you don't do it, how it can be more complicated. Now, maybe this is fine, and it's easy for you to visualize from this 3D initial diagram there, and you can easily remove this for insulation in your head between parts A and parts B. That's great. If you can solve it that way. But the thing to think about is not only can you go back through your work and understand what's going on, but can your grader, your coworker, your teammate go through your work as well and understand what you did. And if you drop something, you mess something up, you don't have as many errors where you've shown your work, and you can double check that, or the grader could award you partial credit. So just a little side note there. So for part A, we're without this insulation layer, so we can go through this large thermal circuit that we have here with everything, but only pull out the ones that are concerned. So we're not dealing with the one that we put a box around here for insulation. So our total thermal resistance with length here is equal to our first one here, our convection term. And then we have plus our conduction through the steel, and then our convection on the outside with the air right there. So we can say that our R prime total is equal to our convection term right here. If we plug in our correct variables, we have 1 over 2 pi Ri Hi. Then for our conduction term right here, we have the natural log of the ratios for that there, which is R2 over R1 for our steel right there. Make sure, again, we're using the right ones for that there. Divided by 2 pi times our K value, thermal conductivity of steel right there, which is what we looked up from our table in the back of the book. Plus now we have our convection term over here at the end, which is 1 over 2 pi R2. Again, pay attention, we're not dealing with the outside, so this right here is our outside right there, R2, H naught right there for our value for our ambient air temperature right there. So this comes from a page 183 for equations for R relating back to your textbook. So now what I've done here, as you can see, boxed in up here is the equation from our previous slide here for our thermal resistance that we just calculated from our thermal circuit, and I have that out all in terms of variables. Now this is where we can see how important it is to have that initial setup page. If we had to go back to the initial problem statement and try to infer all those things with those variables in there, it'd be a little bit difficult and easy to lose something along the way. So what I've done over here on the right is I've taken all the variables that we have on our setup page and put them back here. If you were doing this problem on your own, you could just flip back and have this page next to you as you're filling this in. But so you guys could see it in this presentation here in this lecture, I've included this again from what we have on that first setup page there. So I have my R1, R2, R3, again, all 4 things. I have the variable name with indices, I have the numeric value, I have the units, and I have how it relates back to our physical problem. We can plug in really all we need right now. The first 3 of those, we need the variable name, we need the numerical value, and we need the units for it. So we plug that in there and we say, okay, I need my R1 value right there. I need my HI value right there. So I can say, okay, R1 is my 0.018. Plug that right in right there. My HI value, I come down here, my HI is 400. I plug that right in there. Now, this is why it's important that we've already done this conversion to meters and are not in millimeters, so we don't accidentally plug in. So when we do our unit analysis, everything works out. Now we move on to our second term right here. We're now dealing with conduction. We have our general equation for conduction. We have our ln of R2 over R1 for the steel, the 2 inner and outer radiuses of that steel thickness of the shell there. the layer there. So this is R2 over R1, or R2, we come up here is 0.02 meters, and we have our R1 is 0.018 meters. Now, the thing you know, whether we're doing this as a ratio or not, this is a factor of 10. So if you hadn't done that conversion to meters, you left it in millimeters, you might not catch it in this one here, whereas you would catch it and it would affect your answer in this one here. So something to think about is how you're plugging these in, and if you're doing your unit analysis out with here, it doesn't matter what they are, because they're going to cancel with each other. So things to think about and why unit analysis is very important. Now on the numerator or the denominator of this, we have 2 pi over our KST. Now our KST is what we looked up from table A1 when we interpolated at 280K. Plus now we have over here our last term for the last term of convection here, because we don't have the insulation layer, 1 over 2 pi R2 H naught, or R2. We can look back up here. This is 0.02 meters, and we have our H naught right here for the outside, HO. The outside is 6 right here when we look this up and watts per meter squared times Kelvin. So we can do our unit analysis, double check everything, that it does come out to meters times Kelvin over watts right there. So we'd expect right here for our prime total right there. You can add those values together, combine them, calculator by hand, Excel, Python, MATLAB, whatever your choice is. We end up with now a value for that thermal resistance per length right there of 1.35 meters times Kelvin per watt. So now our next step here is to calculate the heat gain per unit length right there. So we have the resistance per unit length, but if we flip back to our setup page there, what did it ask us to solve for in part A? Well, that was the heat gain per unit length there. So we need our Q prime right here. So we've already taken a look at our general equation, our governing equation for Q prime. This is going to be T infinity outer minus T infinity inner, our temperature of our outside fluid, which is air, minus the temperature of our inside fluid, that cooling pharmaceutical, divided by, there's your R prime total that we've just solved for, that we can plug in directly to this here. We know these values right here's the temperature difference, so I can leave it in Celsius, but if you're not sure, convert to Kelvin. So we do this here, 23 degrees Celsius minus 6 degrees Celsius, all over 1.35 in units of meters times Kelvin per watts. We do out our math right here. We end up with, for our Q prime, or our heat gain per unit length, is 12.6 watts per meter, which are the units we'd expect for heat gain per unit length, watts per meter. Yes, that's correct. Our unit analysis checks out. This is what we want for part A in our problem. Now, from here, we need to go to part B. Part B, the difference is now we want to include this insulation layer and compare the difference between having the insulation layer and not having that insulation layer, looking at that heat gain per unit length right there. So now what we do is we go back to our R prime total right there and realize we now have this new term that we need to add into our previous one right here, which is our conduction value for our insulation. So now right here, where we say our convection right here, I, and our conduction right here remain the same as part A. Now this is something, if you're not quite sure, does that make sense? Do my radiuses changes? Go back through and resolve it. This right here happens that these two remain the same, and if you don't believe it and you want to prove it yourself, just go back through and do it again. It's not going to take long. Better to have the extra work there instead, like solve them separately and not take it for granted. So we go through right here and we want to find our conduction of the insulation to add in there with our convection and our conduction of the steel right there. So now what we see now here is we have this, when we plug this in, is our natural log of R3 over R2 right there. So that's when we go back to our setup page. What is R3 is 30, R2 is 20 in millimeters right there. It's a ratio, those units cancel out, so we didn't have to convert to meters right there, but it doesn't hurt to. Divided by 2 pi times the K for our insulation, which was given to us in the problem statement of 0.05 watts per meter times Kelvin. So I take the natural log of that 30 over 20 divided by 2 pi times our 0.05. What I end up with is 1.29 meters times Kelvin per watt right there that I can plug in now for this value here. Now, what does change here is this here. So we said that this and this don't change, but this is going to change now because it's out a little bit further for this case here. The distances, your radiuses are different. So the outer convection resistance is now given by this relationship here, where we have 1 over 2 pi times our 3. That's the main difference there, and why that one is going to change right there, times our HO. So this is equal, when we plug this in here, we have 1 over 2 pi times that R3. We convert it to meters right there. So rather than 30 millimeters, we're at 0.03 meters times our HO value, which is 6 in units of watts per meter squared times Kelvin. Plug that in, and our convection term now here for the outer convection term is now 0.88 meters to Kelvin per watt. So now we have our convection outer and we have our conduction insulation. So these two terms at the end here of our total resistance, thermal resistance right here, that can now be added in with those two from the first part A of the problem there. So that's what we do. We can add those back in. Our total resistance now is equal to, when we add all those parts together for all 4 of those right there, with these being the 2 new ones that we just calculated, these being the 2 from part A right there, all in those units of watts, all the units of meters times Kelvin per watt right there. So our total resistance now becomes 2.2 right there, and the same units right there that we see now of meters times Kelvin per watt. Now, next we can use this total resistance value that we've just calculated in order to calculate what they asked us to solve for in part B, which is the heat gain per unit length right there. So same equation that we used before. Again, we can convert this to Kelvin right now when we do this out here. So we did it one way Celsius, one way Kelvin, just to prove ourselves. We could do it either way like that with temperature difference, all divided by that our total number right there. So we have our 296.15 minus 279.15 Kelvin, which gives us a temperature difference of 17 K. Do that in Celsius, prove yourself that it's the same way with our Celsius terms right there, divided by that new value for our total resistance right here of 2.2. So now when we calculate this out for our heat gain per unit length, well, including the insulation, we have our Q prime is equal to 7.7 watts